So hello guys, today we are going to solve a Pathfinder question from thermal physics. So this is check your understanding question number 2. This question says a vessel contains Vi equals to 20 liter water at temperature theta I equals to 20 degrees centigrade. When a heater inside the container which can supply heat at a constant rate is switched on, the temperature reached a value of 60 degrees centigrade within a time interval del T1 equals to 40 minutes. Now water of temperature theta I equals to 20 degrees centigrade is slowly added into the vessel at a constant rate of R equals to 200 semi-cube per minute, and then heat capacity of vessel and then heat loss to the surroundings are negligibly small. So we are asked to find how long after the beginning of experiment water will start boiling, and in second part, if instead of water some other liquid having all properties same as those of water except its boiling point is 150 degrees centigrade is used, how long after the beginning of the experiment will the mixture start boiling. The liquid is miscible in water. So for first part we can first see that what happens is after the initial 20 liter volume of water reaches 60 degrees centigrade, additional water is poured up at a rate of 1/5 liters per minute, and the heater is still on. So heat provided by the heater boils up the water initially present, which is 20 liter, and also the water which is coming at a rate of 1/5 liter per minute. So the heater heats up the water from 20 degrees centigrade to 60 degree in 40 minutes. Hence it supplies heat at a rate R dash, which we can find as Vi theta 1 minus theta I rho W into S delta T1, where rho W is the density of water and S is specific heat capacity. So this is the formula of Q equals to ms del T, that formula. So this heater heats up the initial 20 liter water as well as the water coming at 1/5 liter per minute rate. If the final temperature is theta b 100 degrees centigrade, then both initial amount of 20 liter water and water accumulated at 1/5 liter per minute speed got to 100 degrees centigrade. So we can sum their amount of heat by heat supplied by the the heater equals to heat used up by 20 liter water plus heat used up by additional amount of water. Let the time be t when temperature of water is theta b equals to 100 degrees centigrade. So this r dash here, this r dash is the rate of heat provided by the heater. So the r dash into t is equals to Vi rho W into S theta b minus theta 1, because the initial 20 liter was after starting of pouring of 1/5 liter per minute water, its temperature was theta 1, so it goes to theta b from theta 1. So this is it, and the water which is coming at a rate R, which is 1/5 liter per minute, its initial temperature is theta I, which is 20 degrees centigrade, to theta b, which is 100 degrees centigrade. So for it we can write this as R rho W S T theta b minus theta I. So we can put the value of R we found here in this equation. So rho W and S gets cancelled and we get this form, and after this and after just some manipulation, and at the final answer we have to consider the initial delta T1 time also, because it is asked to find the time for the whole of experiment. So initially it was delta T1 which was taken for the 20 liters to get to 60 degrees centigrade, so we have to add up that also. So the final answer is 240 minutes. And for part B, let we assume that the final temperature of the water be theta F. Okay, so we can apply the same concept here, that heat provided by the heater equals to heat used up by 20 liter water to reach theta F plus heat used up by additional amount of water to reach theta F. So we can put this same r dash t equals to vi theta f minus theta 1 plus rt theta f minus theta I. Here OWS, and here also we can write this, but this gets cancelled, so I just ignored them. Okay, so after that we can take the terms containing theta f as common, which is rt and this vi. We can add them up, and the rest terms we can put them to left hand side, and then we get this form, and from there we get theta f equals to this, and then we have to put the values of r dash and r and all. So we can find r dash. Here you can see this, we have excluded the row w and s terms because they got cancelled in the first expression only. So we can have, this is our vi, and this is theta 1, and this is theta I, and this is delta t1. Okay, so that is our r dash without row w and s, as you can see. So from there we can get r dash as 20, and then vi is 20, theta 1 is 60, and r is 1/5 liter per minute. This is t, this is theta I equals to 20, and this is 20 vi plus r 1/5 into t. So you can get that theta f equals to this. So now you can see that as we put theta f equals to 150 degree to boil the system, we get that 330t equals to minus 9000. So this is actually contradiction. Time cannot be negative, so actually this cannot happen. So why this cannot happen? Because we will get some asymptotic value when time tends to infinity. We will get some constant theta f, or you can say this is the limiting value of final temperature as T becomes very large. So you can find that by dividing the right hand side of this expression by t, and then putting that limiting value, limit t tends to infinity, this terms gets to 0, and we can see this is 120. So maximum attainable temperature of this mixture will be something 120. So I guess you could have enjoyed the solution and also learned something from it, and I will try to bring up more challenging problems, and stay tuned. Thank you. Peace out.